It's question show time. Your questions, my answers. Wherever you are on my channel, if a question pops into your brain, just write it out. I will gather them up and I'll answer them here. A few things just before we get into the show. One, stick around to the end. I got another guest, not exactly answerer, but science experimenter. So you're definitely going to want to check that out. Second, happy 20th anniversary to Universe Today. I started Universe Today, March 23rd, 1999. Here I am, 20 years later, still doing the same job. Science, space, communicating. So thanks to everybody who's been reading my work, listening to the podcast, and of course, watching the videos. Here's to 20 more years, 50 years, until I get to my third robot body, until we all watch the end of the universe. So thanks everyone for all of your support over all these years. It's been fun. And the third thing is, I've been reading a book, and I just wanted to, yay, I read a thing, which is, I've been reading The Dark Force, which is the sequel to The Three-Body Problem, and I'm really enjoying it. And I know, like a lot of people, I found the first book interesting. It's translated from Chinese, and it's sort of about, it's sort of like an answer to the Fermi paradox, and it was great. But it was sort of a tough slog. But I got into the second book and people said, no, read the second book. You're really going to love it. And I really love it. So I just want to let you know that if you sort of got through the first book, but you weren't super excited to get into the second book, definitely take a second and get into the second book, The Dark Forest. It's so good. And I'll try to let you know any other interesting sci-fi books that I am reading. I'm spending a lot more time reading these days. So hopefully you'll join me and read some books. All right, let's get into the questions. Captain Video Blaster. Right now, we're not trying to contaminate planets with bacteria. However, if we start to build bases and permanent sustainable settlements, are they going to introduce bacteria in a calculated way so that dominant microscopic species in Mars isn't something like diarrhea? Oh, that'd be gross. Can you imagine that? Like the whole planet is just covered in everything you touch, it's diarrhea bacteria. But I don't think you have to really worry about that, right? That whatever becomes the dominant life form on Mars, if it's even possible, will be whatever is the best situated to exploit the environment of Mars. And I doubt a bacteria that evolved to live in our guts, in the nice, warm, moist environment, food-rich environment of our intestine, is going to be the same kind of bacteria that's going to thrive in the hostile environment of solar radiation and carbon dioxide atmosphere and all kinds of sort of nastiness. So I don't think that's going to be that much of a concern. It's, I think that if there is no life on Mars, then we will deliver all kinds of life forms to Mars. And if life can exist, then Mars will figure that out. Like some life form will try to exploit the environment. But I don't think we have to worry that much. There's very little usable energy that falls onto the surface of Mars. Like it's a fraction of the usable energy that falls on Earth. And so even if in the best possible environment, the Martian ecosystem wouldn't be thriving in the way that Earth does. It's just too far, receives so little light from the sun. So it's actually a really rough place to try and get life going. It's not another Earth. Peter Hoole. Since all life on Earth is related, does that necessarily mean that life had only one successful genesis, eventually evolving into the diversity we see today? Or did it happen innumerable times in different tidal pools or undersea vents and could be happening as we speak? If the former is true, my bet is that all life we find on worlds will also be related and panspermia is the answer. From what we can tell, all life on Earth shares a common ancestor. Every single life form, from me to the trees, to the bacteria, to lions, to everything, flowers, they all share a single common ancestor that evolved at some point. All of the multicellular organisms share a common ancestor, something where, the first multicellular organism was able to exist, and everything at the end of the day, shares some common ancestor. Now, does that mean that life could have formed multiple times? Maybe. We don't know. We don't see any evidence of those other situations. You would expect to see some form of life that is totally different, and we don't see that. And so I think you're exactly right. You know, if we go to Mars and we find that there's life on Mars, we may very well find, oh, what do you know? It shares DNA, and we can track back the common ancestor and find out that, yes, indeed, maybe life moved from Earth to Mars and back maybe multiple times, you know, with asteroids smashing into Mars, blasting meteorites into space. They travel through space, they land on Earth, they spread life to Earth. And it could very well be, as weird as it sounds, that if we find life on another world and we're somehow able to do a DNA analysis of that life, we may find, you know, that the life on Alpha Centauri is somehow connected to us, that there's some form of galactic panspermia. So until we find another example of life, all of these questions are a mystery. We just don't know. We still haven't found anywhere else but here on Earth that has life. And until we do, we just won't know. Matt Zero. To solve the cost problem, let's get other slack-ass countries to pitch in for a change. Most people in the United States don't realize the level of space exploration funding that's going on around the world. So yeah, NASA is by far the largest space exploration budget, but coming in at a close second is the budget spent by the European Space Agency. It's billions and billions of dollars. Think about some of the missions. They've got the Planck mission upcoming. ESA alone has 3 planet-hunting space missions that are coming up. They have astronauts. They contribute to the International Space Station. So does Canada. So do the Japanese. So obviously the Russians. They help build the thing and supply the rockets that get up there. A lot of the space missions are collaborations among countries. The Indians are have sent a mission to Mars. They're launching a mission to the moon. They've just announced they're going to be launching humans to space. The Chinese, obviously, they have a lander on the far side and a rover on the far side of the moon right now, which is an accomplishment that no other country has been able to do. So you would be amazed. The James Webb Space Telescope is going to be launching on a European rocket that's going to be launching from South America. There's the Electron rocket company, which is launching rockets. It's an American country, but they're launching rockets out of New Zealand. There are Australian companies. The amount of investment that's going on around the world is enormous, and almost every large country is playing a part in this. So if you think that this is sort of an American-dominated thing, you would be surprised to know how much of space exploration is happening from other countries. And a lot of the times when the United States pulls away from things, other countries are filling that gap. And so, for example, now the next big international space station is probably going to be a Chinese space station, and they've invited countries around the world to participate on their space station. So eventually the International Space Station is going to come back down to Earth, and then the only game in town will be the Chinese space station. So, you know, I wouldn't sort of think that the way things are today is the way things are going to be in the future. I would say, if anything, we're going to see a future of space exploration to be a multicultural thing, multi-country thing, and that should be the pathway into the far future. Loma Chia. What would happen if a rogue planet entered our solar system but just passed through without any collisions? Would the gravity of the planet wreak havoc around the solar system or make a mess of the Oort cloud, sending asteroids all over, etc.? Yeah, if a rogue planet passed through the solar system, it really just depends on the mass of the planet, the speed that it takes as it passes through the solar system, and like how close it gets to other planets. So if the rogue planet was, say, several times the mass of Jupiter and it passed right through the inner solar system and it went really slowly, you could imagine it causing a tremendous amount of disruption to planets and moons. Asteroids would be scattered around. You know, big things like Jupiter would probably be fine unless it got really close and it was several times the mass of Jupiter, but you could see it absolutely kicking Earth into an orbit that would carry it out of the solar system, all kinds of things like that. So, but if it was smaller and was farther away and moved very quickly and didn't have a lot of time to cause a lot of disruption, then it wouldn't do very much at all. So it really just depends. Now, one of the ideas is that maybe as rogue planets or brown dwarfs or things like that come somewhat close to the sun, within a couple of light years, it can cause a disturbance in the Oort cloud that can send comets down into the inner solar system, and they can smash into planets, including the Earth. And that might be an explanation for why we've seen bursts of asteroid comet impacts in the past because we get too close. And now with the Gaia survey, we can see that if you run the clock forward, you will see where we will get relatively close to other stars. And it actually happens more often than people were thinking. So it's definitely a concern. I think the next big issue will happen in like 70,000 years from now when we get pretty close to another star. So I guess just keep watching. Leo da Silva. Great show. What's the speed of 1G in kilometers per hour? I tried to find it in Google, but there seems to be no understandable answer for a layman. No problem. And the reason is because 1G, one gravity, is actually a force of acceleration, not a velocity. So here I am standing on the Earth. I'm being pulled by the entire mass of planet Earth, and I am experiencing 1G. That feeling that you are accustomed to at all times, everywhere you go, is 1G, 1 times the force of gravity. Now, if I was to get into an elevator and go up very quickly, I would feel heavier. And that would be, you know, probably wouldn't be 2Gs, but it would be more. And that is because not only am I experiencing the downward force of the Earth, but I am also experiencing the downward acceleration from the Earth. I'm also experiencing an upward acceleration from the elevator. And then as soon as the elevator stops accelerating and it's just moving at a constant speed, then I don't feel that extra gravity anymore, that extra sort of pull down. And so it's important to really understand that. And so that speed is 9.8 meters per second squared. So in 1 second, your speed increases by 9.8 meters. Then 1 second later, your speed increases by another 9.8 meters. So now you're going 18 meters per second, and then you're going 27 meters or whatever, 30 meters per second, and then you're going 40, right? And that's that acceleration. It's only when you feel acceleration that you'll actually feel G's. And so if you want to be in some spaceship and you want to experience 1G of force to essentially counteract the weightlessness of being in space, then your spaceship has to constantly accelerate and go faster and faster and faster and faster. It can never coast. The second it coasts, then even though you could be going at a significant percentage of the speed of light, you're going to feel weightless. Raymond Ross. If neutron stars are the absolute limit of matter being packed before going black hole, how can we not have more black holes in the past? We go farther and farther back, matter is more packed, so boom, neutron stars, black holes, ramming into each other, more black holes. Did inflation solve this? All the matter we see, which is a tiny percent I know, packed into a singularity or something, then inflation happens and we get neutron stars today, black holes if the mass of the star is large enough. But roll back and I just wonder, are there more black holes that we know? I mean, isn't neutron star state the absolute limit of packed matter before going black hole style? Make some sense for me, please. All right, so the question that you're really asking, I think, is why wasn't the early universe, when it was packed together in this incredibly dense state, why wasn't it just a black hole, right? How could it have been less, if it was packed as tight as a black hole, how come it's not a black hole? And the reason is that a black hole is caused when you've got a difference of density. And that early universe was equally dense for maybe ever, right? It could have been infinite in all directions of this incredible density. And then inflation happened and things expanded and it went on from there. And so without those differences in density, you couldn't get that black hole forming. That's the first part. Now it's possible that there were, in the very early universe, there were places where as that initial expansion was happening, and you were sort of after the Big Bang and things were becoming less dense over time, that there were like folds, Holdy folds, where you had like a little bit more density. And it's possible that that density could have caused like primordial black holes to be formed, because even though the entire universe was expanding and you didn't have those large density differences to just turn everything into a black hole, you could still have like little localized areas. And this is one of the ideas that astronomers have, is that maybe out there are these primordial black holes, or maybe primordial neutron stars that are left over from the Big Bang. And we could theoretically see them as they evaporate over time. So maybe there's one out there with the mass of a house and it evaporates. And maybe there's one out there with the mass of the moon or the mass of the Earth. And then beyond a certain point, and maybe they served as the seeds of the larger black holes that we see today. But there's no evidence for that right now. It's an idea that some people entertain, but no one is, not many people think that they exist. So that's why everything isn't in one big black hole. Furious George. If I were to levitate just a few inches above the ground and not move, would the Earth move underneath me, or would it be pulled by gravity to go along with it? All right, so I'm going to assume that there's some magical force that is causing you to levitate perfectly above the Earth a couple of inches. And whatever that force is, let's imagine that there's like a rope pulling you, there's a tractor beam that's pulling you, that's keeping you just above the surface of the Earth. What that would do, and it would be imperceptible, is that you would be slowly pulling on the Earth with your gravity. Now, the Earth is trying to pull you with its gravity, but some force is stopping it because you're levitating. So therefore, your force pulls on the Earth. Now, is the same thing stopping the Earth from getting closer to you? If so, then you would actually start to pull the Earth through space. Now, it would be an imperceptible amount. It would be nanometers every 1,000, I don't know what the number is. It would be tiny, right? You could never measure it. But over time, over trillions, quadrillions of years, you would be pulling the Earth around like a magnet, which is a pretty great idea. Now, a bigger version of this is one of the ideas that's been thought of to move asteroids. So if you have like an asteroid that's dangerous, you want to get rid of it, you want to move it to a safer orbit, you park a spacecraft really close to the asteroid that has mass, and then it fires its ion thrusters or rocket engines or whatever for a long period of time and continues. And what happens is the asteroid is pulling on the satellite, and the satellite is pulling on the asteroid. And because the satellite is using its rockets to counteract the gravitational pull of the asteroid, its gravity pulls at the asteroid. It's called a gravity tractor. And in theory, over long periods of time, you could slowly pull an asteroid purely through gravity away from a dangerous orbit into a safer orbit. So it's a pretty cool idea to think about. Larry Fields. Is there any truth to these super planets that are just outside the Kuiper Belt, the ones they are claiming coming into the inner solar system? I think one was called Nemesis or Planet X that has appeared in other YouTube channels. No. This idea of Nemesis or Planet X or Nibiru does not exist. It is a hoax. Hoax. If there was a planet that was big and could cause the Earth to flip over, it would be one of the brightest objects in the night sky. Every astronomer, you can even see with your own eyes, if it was any closer than Saturn, right? And of course, astronomers have telescopes that let them see things that are thousands of, that are hundreds of astronomical units. I think the most distant thing now is like far, far out, and I forget the distance, but it's ridiculously far, 120 astronomical units, something like that, really far away. And so, and it would take tens of thousands of years for something like that to make its way into the inner solar system. So it is entirely possible that there are large objects out there farther in the solar system beyond the orbit of Pluto and so on. It's just that they are orbiting the sun like all the other planets, and they're not going to get any closer to us and cause us any danger. So there will come, I hope there will be a time when we will, people will be able to announce the discovery of a new giant planet out in the Kuiper Belt, but there's no risk from it. It's not dangerous. And so the problem is that people are just literally making things up to scare people for conspiracy theories. I'm not sure why. Anyway, I've been debunking this idea, this Planet X Nibiru thing, for 20 years. And I'm sure I'll be doing it for 20 more years. So it's not there, it's not real, it's not happening, don't worry about it. James. Hey Fraser, I'm really hoping that you can answer my question, as I've been wondering about it for days. When Webb uncovers the baby galaxies, are these the farthest objects we will ever be able to resolve other than the cosmic microwave background? Are there fetus and embryo galaxies after that? Could we even get so far as to be able to see individual stars forming before they become galaxies? Thanks. Yeah, so James Webb is, when James Webb launches, right, one of its jobs is that it will be so powerful that it will be able to look right out to the edge of the observable universe and see the first galaxies coming together. And that right now, those early galaxies, Hubble can see them, but it has to do a bank shot with gravitational lensing. So it uses a galaxy or a galaxy cluster that's closer to act as a natural lens so that it can see this galaxy that happens to be moving behind this galaxy cluster. And so it can see these right at the outer edge of the universe. When James Webb launches, it'll be able to do this directly in any direction that it wants, which is going to be a big time saver, right? It'll let you choose a place you want to observe and then just observe it, as opposed to waiting for nature to line things up perfectly for us. But you're exactly right. That is not the best thing that we could see. The next step that we would want to see is to be able to see the first stars forming. And there are these ideas of these first initial, they call them population 3 stars, those first stars when all there was in the universe was hydrogen and helium left over from the Big Bang. They gathered into enormous stars and detonated as enormous supernovae. They didn't live long, and we have not been able to see them directly. We understand that they're there, but we don't see them yet. And so future monster space telescopes like LUVOIR are going to be the next generation, and their job will be to help see those first stars that are forming. So even after James Webb, there's going to be lots and lots of room for even more powerful telescopes to do this work of seeing right to the edge of the observable universe. And then the cosmic microwave background is sort of the wall that we can't see beyond. Drogo Baggins. Building a collider that could destroy the universe? Oh please, there's no way that we can ever come close to the energies and collisions that happen every time two neutron stars collide. This is based on the interview that I did with Phil Torres about existential threats, and that's a great point, right? That there are far more powerful collisions that happen in the universe than anything we can do here on Earth, right? And yes, probably, almost certainly, the chances of us turning, starting off the vacuum energy cascade or turning the universe into Ice 9 or whatever, right? Something like that is incredibly remote. But the issue is that the consequences, if we did something like that, would be terrible. And so we should be cognizant of, as we explore these new technologies, to think about the implications. And CERN has gone through, I think, a really great process, right? Someone said, if you generate a black hole, will that drop a black hole? If you generate a microscopic black hole and that drops into the Earth and eats up the Earth from the inside, is that a risk? And CERN said, probably not. And so, but then they went and found an example where you have particles crashing into the Earth's atmosphere from supernova or whatever is causing them, that is generating the same kind of energy as the Large Hadron Collider. And so then they said, see, this demonstrates that this exact kind of collision is already happening all the time here in the Earth, and the Earth is still here, so our experiment isn't going to cause this risk. And I think that's just the step you've got to take, is to say, if you're going to do some kind of experiment, you should at least try to figure out a reason why, if there is some existential threat in what you're doing, that you should at least be sure, or at least have thought about what are the implications of the experiment that you're about to attempt. And because the consequences, however remote, are bad, super bad, right? You destroy the universe, right? Should have taken a second just to make absolutely sure that you weren't going to destroy the universe. And if it's possible that your experiment is going to destroy the universe, you should just do a little extra math and just make sure. And so I think that as we move into these new technologies in artificial intelligence and bioengineering and nanotechnology and climate destruction and large physics experiments and things like that, that more time needs to be spent thinking about what are the consequences for us doing these experiments, because it could be that one of them is bad. And so let's try and figure it out in advance. Let's at least stop and think about it before we go crazy and just do it. That's all. Debutin. These videos are getting much better. Less FaceTime, more 4K footage. Keep it up. Thanks. Back when we started these episodes, I would look at the camera and I would do my explainery, and we would have maybe 6-10 pictures that showed up in a little corner of the screen. And now, my videos are longer. They're 13 minutes long, 10 to 15 minutes long. And they're almost entirely filled with full screen video and pictures and animations and things like that. And that's just thanks to Chad for finding all these amazing footage to work with, thanks to NASA, thanks to ESA for being able to supply a lot of the photographs and video and stuff that we're able to work with. And it's actually a lot easier for me because I don't have to, I could just record directly into the microphone. I don't have to turn the camera on. But at the same time, I think it's, you know, I've had a couple of people complain and they said, like, we don't see the person who's behind these videos anymore. And that's because for some of them, I don't even bother turning on the camera now. But I do keep the camera going for the question shows. So I think if I have more time, I will try to embed like a little bit of me, at least so you know that there's a human being here who's doing these videos. But give me your feedback. Let us know how you feel the quality of our videos has changed over time, if the topics, production, anything. Let us know. Always give us feedback. We can take it. Okay, something special for you this week. Normally I try to get a guest answerer, but instead I have a guest science experimenter. It's Jenny Ballif, aka Science Mom, and she's gonna do a demonstration specifically for this show about how you can combine light in really interesting ways to make different colors. And it's a very cool demonstration of just how light works.
Hi everyone, my name is Science Mom, and today I have a fun, simple science activity to share with you about light. I'm using spotlights and soup cans that I cut both ends off, but you don't need to use spotlights. You can also use flashlights and colored balloons. The model for color that we learn when we're in elementary school or primary school is subtractive. You have red, yellow, and blue as your primary colors, and the more colors you mix together, the darker the colors get. And this is because when something appears, say, the color blue to our eyes, it's absorbing all of the wavelengths except for blue light, which it reflects. And so if you mix together two different colors, then the amount of light that they are absorbing increases and they are reflecting less light. But when you're talking about mixing light, it's very different and very surprising. So this activity that we're going to do with colored spotlights is a fun way to teach about how when you add wavelengths together, you have additive rather than subtractive phenomenon, where the more colors you add together, the lighter it gets and the closer that you get to white. Here's a red and green spotlight. Now, if this was colors of paint and we mixed red and green together, we expect to get brown. But with light, these colors mix to create yellow. Here, the primary colors are not red, yellow, and blue. They are red, green, and blue, hence the RGB color system that we use in our electronic devices. Red and blue mix to make magenta, blue and green mix to make cyan, and then, like we said before, red and green make yellow, and then in the middle we have white. You can see that if I move these spotlights so that they overlap completely, they really do appear white. But unlike a white spotlight that casts a gray shadow, the shadows from my red, green, and blue spotlights play out in a rainbow. This is so much fun. When I do school visits, I have 4 spotlights with colored cellophane draped over them. I add in yellow as well as red, green, and blue because adding in the yellow improves the color just a little bit more and gives a little more depth to the shadows. I hope you enjoyed this simple science demonstration. It's a great way to teach about light, and again, you don't have to go out and get spotlights and cellophane. You could just get some colored party balloons, stretch them over flashlights, and then you're good to go with your own miniature spotlights, and you can have a lot of fun teaching about light or just making awesome colored shadow puppets. Back to you, Fraser. Thanks a lot for having me on.
All right, thanks, Jenny. That was awesome. I know it was a little different than what we normally do, but it was great to be able to include that. And please, go check out Jenny's channel. If you've got children and you want to be able to come up with experiments that you can do to show them how to do more, you should totally subscribe to what she's doing. All right, so that was super fun. 20 years. Here's to 20 more or more. As always, wherever you are on my channel, if a question pops in your brain, just write it down. I'll gather them up and I'll answer them here. All right, I'll see you next week.